Okay, so this is part 2 of our buffer notes. So we're talking about solutions that are buffers, and what happens to be a solution that's a buffer? And the question is, what is a buffer? So all a buffer is it's a solution that is prepared in or is just naturally there. And what does it do? It maintains what? The same what? pH. Awesome. So what it does is it takes away either the hydrogen ions or the hydroxide ions so that it can maintain that particular pH. And buffers can be made in 2 ways. Buffers are either made by having a weak acid with its salt or a weak base with its salt. So any one of those situations will give you a buffer. And what we're going to be talking about today is an equation that helps, and it's called the Henderson-Hasselbach equation. I absolutely love the Henderson-Hasselbach equation. So we'll come to that in 1 second. In this question, what we're first going to start with is it says, in each case below, indicate which salt will form the more acidic solution. So if we want something that's going to be a little bit more acidic, then do we want the pH to be low or the pH to be high? Lower pH, okay? So what we want is we want a pH that's less than 7 if we're talking about something that's more acidic. All right, so here's how we do this. Remember, what we do is we're going to split this up, and we're going to write H what on top? HOH. Awesome. And we're going to do the same thing on this one. We're going to write HOH. What we're going to do is, you don't have to write all of them out, but you're going to look at it, and what's HNO3? Well, is that a strong acid or a weak acid? We know it's an acid, right? So let's review our strong acids again. It's what? I-clobber, No3, Clo4, Sulfur. So it's H with one of these, okay? It's H with one of those. And then we said our strong bases are all of the 1A's, and then what in the 2A's? Caserba, awesome, with hydroxide, okay? So this is the only one, by the way, that's diprotic, meaning that it has 2 protons or 2 hydrogens. So we don't have to write these all out, but HNO3, would that be strong acid or weak acid? Strong acid. So we've got a strong acid plus, what about NaOH, strong or weak? Strong base, right? Sodium hydroxide, so that's a 1A with hydroxide. So if you have a strong acid and a strong base, what would you expect the pH to be about? 7. This one should be about neutral. That should be about 7. Let's test this one now. So now we've got H with NO3 again. So what's H with NO3? Strong acid. What about Fe with OH? So it's going to be FeOH3. What about that? Strong or weak? Weak. It's not one of the strong bases. It's not a 1A or caserba. So what would you expect the pH of this one to be? Lower. This should be more acidic. So in that case here, if they're asking us which one's more acidic, your answer would be FeNO33. Okay, let's try the next one, letter B, right down here. Again, you're going to write an H and an OH, and you're going to do the same thing here. You're going to write an H and an OH. So let's do the first one. We've got HBr. Is that a strong acid or a weak acid? Strong. I-clobber. So that's our strong acid. What about KOH? Is potassium in the 1A's?
Yeah.
Yes. So that's also a strong base. So that would give us a pH of about 7. Awesome. So now let's try this one. HBRO. Strong or weak? What do you think? Weak. It's not on our list. So that's a weak acid. What about KOH? Strong base. So you would expect the pH of this to be more basic. That's higher. So which one's more acidic? This one is considered more acidic. Okay? It's probably not acidic, but it's more acidic than the other one. Okay, so you can see that the way that we work these problems out, because you would look at these and it's a multiple choice problem, and you look at it and you're like, what? Why would that be an acid and why would that be an acid? And so if you saw that on a test, you'd probably go, I don't know what they're talking about, I'm letting that go. So what you're going to do is you're going to break it up, you're going to make your H and OH, and then check to see strong or weak, check to see here strong or weak. So let's try it one more time here, okay? Well, where does this one break up? That's kind of weird. But do you see your negative charge on here? What do you think the negative is? The chlorine. That's actually where it splits off, is right there. Okay? So to the left, we're going to do our H, and to the right, we're going to do our OH. All right, the first one is HCl, strong or weak? Strong acid. So what do you think this other one is? Weak. Perfect. So strong acid and weak base, that makes it more what? Acidic. Okay, and then this one here, we're going to do the same thing. We've got HOH, we've got HCl again. So again, we have a strong acid. What about Ba with OH? Strong. Why strong? Casurba. So that would be barium hydroxide, BaOH2. So that's a strong base. So we'd expect this pH to be, yep, about 7 again. So which one's more acidic? The one on the left. All right? We got this? Let's continue on then, okay? So now let's talk about Henderson-Hasselbach. So this is an equation that is used in medicine. So they do actually have equations where medical students will be asked and they plug in the equation and they try to figure out if there are issues with the acidity of blood, then they will use this equation to try to figure some stuff out here. So this equation, pH equals negative log Ka, and then it's HA over A. But we're going to memorize this, okay? And the way that we're going to do this is we're going to say pH equals pKa plus log of Cb over A. And here's why. This here is your acid, and this here is what we're going to call this is HA, which is this is your conjugate acid, and this is the actual acid because this is your H plus, and that would be your A minus. So if it has the H plus in it, this is called your acid. And this here is your conjugate base. So remember, what comes off of your acid we call the conjugate base, okay? So we're going to say pH equals pKa plus log of Cb over A. Ready? Do it with me just one time. Here we go. pH equals pKa plus log of Cb over A. Now, that's the pH equation. If you wanted the pOH equation, so let's say that instead of having an acidic buffer, you actually had a basic buffer, it would be the same thing. But instead of pKa, it would probably be pKb plus log, so it's pOH equals pKb plus log of, it's still going to rhyme a little bit, Ca over B. Okay? And it's the concentration of your conjugate acid over your base. So this would be your base, whatever your base is, and this would be the conjugate acid, which is the salt. So this is going to be your weak base and it's salt, or a weak acid and it's salt. Okay? So that's how this equation is going to work. Everybody just say this one time. pOH equals pKb plus log of Ca over B. Okay? So where this is, say it one more time. pH equals pKa plus log of Cb over A. Okay? So the actual one is on the bottom and then the salt is on top. So what is a buffer? Again, all a buffer is it's a weak acid with its salt. Or it's a weak base with its salt. So what they call the conjugate acid or the conjugate base, that's also called the salt. Okay? So I'm going to come back to this in one second. Actually, it says that half the equivalence point is the volume where your pH and your pKa are equal to each other. Why? When would your pH equal your pKa? If these two are equal to each other, go ahead and type into your calculator, what is the log of 1? Anybody know? What's the log of 1? 0. So if these two are equal to each other, this entire thing ends up being 0, and so your pH and your pKa are the same. So at half the equivalence point, that's where your volume of your concentration of each one of these would be equal to each other, and that's just something if you were on a graph or looking at a multiple choice problem, if they asked you something like that, that's something good to know. So if you guys want to write that down too so that you have it. All right, let's try to use this equation. So first thing is, this is a review problem. This is not using the equation just yet. This has 1 liter of pure water is at a pH of 7. If you add 0.1 moles of sodium hydroxide, the question is, what is the pH now? Okay, so we just have water, and then we're going to add 0.1 moles of NaOH, which means, what's our new molarity? The molarity of our base is equal to 0.100 moles over our 1 liter, which means that we have a 0.1 molar NaOH solution. Do you agree? Yes? Okay. Well, if we were going to write this, we would write that NaOH breaks up into Na plus and OH minus. So if this is a 0.1 molar solution, then after it has dissolved in the water, if it's a strong base, how much of this NaOH is actually left? 0. Awesome. None of it. So what's the concentration of our Na plus? 0.1. And what's the concentration of our OH minus? 0.1. So with that helps. The Na plus we don't really care about, right? But what can we do with the OH minus? You can negative what?
Log.
Negative log. And if you negative log your OH minus, what does that give you? POH is negative log of OH minus. So if you just plug in your 0.100 into there, then what do you get? Well, that's 1 times 10 right to the negative 1. So if it's 10 to the negative 1, then what is your POH equal to? 1. Perfect. But we want 3 sig figs, so not 1, but 1.000. 3 sig figs, remember only the numbers after the decimal count. That's your POH, so what would your pH be equal to? 13.000. Does it make sense? Should a base be at a pH of 13?
Yeah.
Yes. Remember, you always want to check that because otherwise the lowest it could be is 7 if it's a base. Okay? If it's an acid, the highest it can be is 7. If it's a base, the lowest can be a 7. All right, this is what is the pH of a 0.1 molar calcium hydroxide solution. So same thing here, but the only difference is now we've got CaOH2. So when it breaks up, we've got Ca2 plus and how many OH minuses? 2. So if this is a 0.10 molar, the Ca is a 0.10 molar, we don't really care about that. What's your hydroxide concentration? 0.20 molar. Good, it's double. Remember, that doesn't work the same way for acids, but for bases, that does work, okay? So in this case, when we write our POH is equal to negative log, well, it's negative log of 0.20. So go ahead and plug that into your calculator and tell me what you get. So negative log of 0.2, and what POH do you get? Okay, so we got 0.70. So then what's our pH equal to in this case? 13.30. Awesome. Okay, and that also is basic. That checks. That looks good. So those are old types of problems. I just wanted to make sure that we're okay with this. What happens if you have a strong acid or a strong base, and an acid will work the same way, except for you would be calculating pH. So it says you have a buffer, and it's prepared from 1 liter of a 0.5 molar acetic acid solution. So I know this is a weak acid, because sometimes they don't tell you it's a buffer, but you're going to see it's a weak acid, and you're going to add 0.2 moles of NaC2H3O2. How do you know that that is its salt? So if this is a weak acid, by the way, that's the acid, what would you call this of it? You would call it the conjugate what? Base. Awesome. This would be your conjugate base, and this would be called your acid, okay? How do you know that this is the salt or the conjugate base of this? Because they both have what? The acetate in it. Awesome. They both have the acetate in it. The only thing is that this is going to be different. Your 1A, your positive cation, that could change. That could be different in front of it. And it would always still be called the salt of it, okay? So after the hydrogen comes off and it attaches something else, that's what's called the base of it or the conjugate base of it. So it says assume there's no volume change. What is the pH of the solution? And then they give us the Ka of this HC2H3O2. There are 2 ways to solve this problem. I first want to show you how easy the Henderson-Hasselbach is. Okay? This is going to be using the Henderson-Hasselbach equation. So everybody write it down. So the HH equation is, everybody say it, pH equals pKa plus log of CB over A. Awesome. Okay? So now let's plug in what we know. What is P? Well, it's the same thing as pH. So when you do, what is it? Negative log, right? So when we do pH equals, P is negative log, so that's all the P is. And now we need our Ka. Do we know the Ka? Is it given to us? Yeah, it's right there. It's that 1.8 number. 1.80 times 10 to the negative 5 plus the log. Our conjugate base. It's a 1 liter solution, okay? And we've got 0.2 moles of it. So does that change then? What's a molarity? It's just 0.2, okay? So it's 0.200 molar divided by the acid's concentration. Again, it's still 1 liter, so what would that be? Still just 0.5 molar. So go ahead and plug this into your calculator. So, okay, and what did you get for your pH? 4.35. Awesome. Oh, we want 3 sig figs, so let's go out one more number. 4.347?
Yeah.
4.347. Awesome. Okay. Now, you could do this without, and this is why the AP has removed this equation. They no longer have the Henderson-Hasselbach. It just takes a lot longer. So what you basically could do is, if you're given a Ka for this, then we can write an equation for it and write an expression. So if we do that, it's nice because it reviews what we did before when we were doing Ks. So we've got HC2H3O2. It breaks up into H plus and C2H3O2 minus. And you need to know how to do these problems anyway. So in this case, it's giving me that my Ka value is equal to 1.8 times 10 to the negative 5. This stuff right here, this NaC2H3O2, when this splits up, it's going to break up into Na plus and C2H3O2 minus. And they're telling us that this is 0.2 molar. So this is 0.2 molar, and this is also 0.2 molar. And this matters to us because in this case here, we have a 0.5 molar of this. 0.500 molar, yes? How much is splitting off? We don't know. So what do we call it? We call it X. And that's X, and that's X, and this is 0.5 minus X, right? Because this is going to dissociate. Now this, if you're adding this to it, and you know that it's a 1A, we know that 1A's are very soluble and it's going to dissociate. So this is actually not X, this is X plus what? 0.2. And we're going to assume that X is so small that it's actually equal to what? 0.2. So this is approximately equal to 0.2. So we're not going to use that, we're just going to use 0.2. So now we're going to write our expression. So we say that Ka is equal to, it's H plus times C2H3O2 divided by H, C2H3O2. So let's fill everything in. Our Ka is 1.80 times 10 to the negative 5th, and that's equal to X times 0.2 divided by 0.500 minus X. So this we can basically say is 0.500 because again, we can say that this X is so small that it's not going to make a difference. So if we work this out, 1.8 times 10 to the negative 5th, e negative 5th, and we multiply that by 0.5, then I get 9, are you getting 9 times 10 to the negative 6? Okay, so 9.00 times 10 to the negative 6 is equal to X times 0.200. And then we just have to divide by 0.200 on both sides. How much longer is this taking? A lot, right? Divided by 0.2, and we get 4.5 times 10 to the negative 5th. Well, that's equal to X. And I know that X is my H plus. So this is equal to X, but it's also equal to my H plus. So what do I need to do in order to get pH? Negative log your answer, and guess what you get? pH equals the negative log of my H plus, which is what I just found right there. And what do you get? 4.347. Did you get the exact same answer? Yes. So that's why they don't give you the Henderson-Hasselbach equation, but in my mind, I would rather that you knew this. Even if they don't tell you it's a buffer, if you get a weak acid and its salt or a weak base and its salt, this is amazing to use, okay? This is something that's going to be really nice to use. So let's try another one. All right, so it says, remember the purpose of a buffer is to maintain a constant pH. So what we haven't done yet is we haven't added anything to the buffer. So the question is, what happens when you have a buffered solution and you add acid to it or you add base to it? Well, it's going to change the pH, but is it going to change it a lot? Yes or no? If it's a buffered solution, is it going to change your pH a lot? No. You can add a really strong acid, and what it's going to do is it's going to maintain constant pH as best as it can. If you add an acid, it still will lower the pH, and if you add a base, it still will raise the pH, but only slightly, okay? So it's not going to raise it by a lot. So it says when you add acid to a buffer, your H plus concentration increases. We know that acids give off H plus. And so it causes your acid concentration to go up and your anion concentration decreases. So what happens to your pH? Your pH, when you add acid, your pH will always go, what? Down. So it decreases. And the opposite, when you add base to a buffer, your pH is going to increase. It's going to go up. All right, so let's try this. So this has a 1 liter buffer, and again, we've got an acid, we've got an acidic solution. Okay, so what we're gonna do here is we're gonna first write our Henderson-Hasselbach equation because we can. They're telling us it's a buffer, we've got a weak acid, and we've got its salts. So we're gonna write, everybody say it with me, pH equals pKa plus log of Cb over A. Now we're gonna fill everything in. So our pH is equal to negative log, don't forget the negative log part, okay, that's the P. The Ka, they told us, again, 0.80 times 10 to the negative 5, and then plus log. The conjugate base concentration, they're giving us the concentration, so we don't have to change anything. It's 0.8 molar and 0.70 molar, 0.700 molar. So go ahead and plug it into your calculator. And you should get 4.803 as your pH. So this is your pH. Here's the second part of the question, and this is what we are talking about. Let's check to see what happens if you add 0.1 moles of sodium hydroxide to it. What do you expect to happen? Well, if you have a buffer that's an acidic buffer, what do you expect if you add a little bit of base to it? Your pH should what? Your pH should go up. So pH should go up. Again, it's a buffer, so not by a lot, but by a little bit, our pH should increase. So here's how we're going to do this. We're going to use the same equation, pH equals pKa plus log of Cb over A. We're going to use the same equation. Okay, so what we're going to do is, first we're going to write a dissociation equation of this HC2H3O2. And what it breaks up into is H plus and C2H3O2 minus. And this is what we're basically calling our acid, and this is what we're calling the conjugate base in this case. So it's the same as what we were doing before. And this, the concentration originally was at a 0.7 molar. And the concentration of this was at a 0.800 molar. Now, if we add 0.1 moles of the base to this, then what it's basically going to do is it is going to react with the acid. So we know that acids and bases will react with each other, and so that's how you form neutralized solutions. But in this case, by adding this base, because it's a buffered solution, it is going to try to maintain the same pH. It's still going to increase slightly, but not by that much. So we know it's going to try to maintain constant pH. So because we're adding a base, the base is going to react with the acid, which means it's going to take away from the acid. And we're going to assume that this is a 1 liter solution, and so we're going to say that it's a 0.1 mole per liter, that there's no volume change is what they're saying. So we're going to subtract 0.100 molar. And on this side, we're actually going to add 0.100 molar. So whichever side that it's going to react with, if it's a base with an acid, you're going to subtract. If it's an acid with an acid, you're going to add on that side. So in this case, we get a 0.600 molar, and in this case here, we get a 0.900 molar. And all you have to do now is, when you fill in the equation, it's all the same. Negative log, same as what we have up here, 1.8 times 10 to the negative 5th, plus the log. Instead of 0.8 and 0.7, now it's 0.9 and 0.6. So we've got a 0.900 molar and a 0.600 molar. So go ahead and put that into your calculator, and what you should get that the pH is equal to is 4.92. So what we can see here is that yes, our pH did increase, but it just increased slightly. So it didn't really increase very much. So in this case here, this is the same as the other one, except for now, we are not going to first calculate the pH of the original solution of the buffered solution. We're just going to be calculating the final pH. So we've got a 1.5 liter of a buffer, and it contains 0.75 molar of the HBRO and 0.850 molar of the NABRO. And then they're giving us the Ka value of this. And they're asking us, again, what is the pH of the solution when we have 0.250 moles of the HCl being added to it. So again, our equation is simply the pH equals pKa plus log of Cb over A, since we're still doing our pH on this one. So let's write our equation here, and we've got HBRO, that's our acid, that's the weak acid that is making up this buffered solution, and it's going to break up into H plus and BRO minus, which this is our acid, weak acid, and this is considered our conjugate base again. So we're starting off with this being a 0.750 molar solution. And this is a 0.850 molar solution because, remember, it's a 1A, the sodium, and so it splits up every time that it ionizes, and you have a 1-to-1 ratio of your Na to BRO. The BRO is what matters. The Na plus is not mattering here, and so that's what we're going to write on our concentration there. So now we have our two concentrations of our acid and its conjugate base, or its salt. So now it tells us that we're going to add 0.25 moles of the HCl to it. The problem is we need molarity. So what we're going to do is we're going to divide this by the 1.5. So over on this side here, we've got a 0.250 mole divided by the 1.50. So 0.25 divided by the 1.5 gives us a 0.167 molar HCl. So that's actually the amount. Well, if I'm adding acid to acid, then what it's going to do is it's simply going to add to my acid side. It's actually going to take away on my conjugate base side. So what's going to happen is the HCl is going to split apart because we know it's a 1A. And so this is actually broken apart. And it's going to, the H is going to react with the BRO. So instead what's going to happen is I'm going to add on this side. So I'm going to add a plus 0.167 molar. And on this side, I'm going to subtract a 0.167 molar because, again, what happens is the HCl breaks up, HBRO is weak, and so this actually wants to come together. So it's going to grab onto H pluses. And so in this case, we're going to subtract because it's going to react with our BRO minus and leave us with less BRO minus and more of the HBRO. So we've got 0.75 plus 0.167, and that gives us a 0.917 molar. And 0.85 minus the 0.167, and that gives us a 0.683 molar solution. That's it. Now all we're going to do is plug it right back into here. So again, the P is the negative log. The Ka they give us is 2 times 10 to the negative 9, plus the log of our conjugate base, which is the 0.683, divided by our acid, which is the 0.917 molar. And now we're going to plug it into our calculator. And what we should get is a pH equal to 8.57. So that's basically it for doing these buffer problems. And so again, if you're adding acid to an acidic buffer, then you're going to add on that side. If you're adding a base to an acidic buffer, then you're going to subtract. If this were basic and we were using our pOH equation, the way that this would be different is if you have a base and you add base to it, then it's going to add on this side and subtract on this side. If you're adding acid to a base, it's going to react with the acid, meaning it's going to decrease your acid concentration, so you would subtract on this side. So it's really just a matter of thinking about it. And then the question is it going to increase your pH or decrease your pH? Again, if you add base to anything, even if it's a buffer, it's still going to slightly increase your pH. And if you add acid, it's going to slightly decrease your pH. All right? And that's it for our buffer notes.